Of all man-made devices, we can say that the metal oxide semiconductor field effect transistor, known as the Mosfet, is the one most frequently used in our lives today. Although we may not realize it, we use billions of them in our computers, our mobile telephones, our games consoles. They can also be found in cars, in electrical appliances, and in the most unexpected places. Basically, they're found in systems where information is processed or stored. Ancient peoples already used communication systems where a small set of different and well-defined symbols or states were combined. The simplest of these is the binary system, which needs just two symbols for communication. Each state is described with a 1 or a 0, according to what has been agreed by the communicators beforehand. An electrical switch is an example of a system that processes and stores information. An electrical switch has two possible states, on and off, and so it can transmit and store information in the same way as more rudimentary procedures. A switch is off when an electrical charge can't flow through it, so there's no current. In the on state, a charge can flow, creating an electrical current. In order to store and manage huge amounts of information in the least space, these switches need to be manufactured as small as possible. A microchip can contain billions of them. However, tiny as they are, they still have to work as electrical switches. There must be a path for the electrical charge to flow, and some electrical mechanism that will allow or prevent the flow of this current. This minute switch is the Mosfet. The Mosfet controls the electrical current flowing between one contact, known as the source, and another known as the drain, by applying electrical voltage at a third terminal known as the gate. By modifying the electrical voltage applied to the gate, a conducting channel can be made to appear or disappear, allowing the device to be switched on or off. The Mosfet is manufactured in a silicon substrate, one of the most prolific materials in the Earth's crust. The advantages of using a semiconductor material are the following. Firstly, we can change its conduction capabilities by the controlled addition of impurity atoms. Secondly, it can have charged particles of different electrical signs, according to the type of impurity added. These particles are called electrons and holes. Electrons having a negative electrical charge, and holes having a positive charge. The final advantage is that in the same small piece of semiconductor, we can create regions with different types of impurity. If we manufacture a structure with regions alternating the two types of impurity, we can isolate the charges of one sign from charges of the opposite sign. Barriers between the regions appear, preventing the charge from flowing from one region to the other. In this situation, there is no electrical current. A similar phenomenon takes place when we want to move a liquid between two containers. Even if the containers were placed at different heights, the barrier would prevent the liquid from flowing between them. In order to have a flow between the containers, the barrier must be lowered. That's the role of the gate contact in the Mosfet, to lower the barrier. The gate contact is made by using a highly conductive material separated from the semiconductor by an insulator. By applying a suitable voltage at the gate, the electrical charge can be attracted from the source. As a result, the barriers preventing the passage of the electrical charge are lowered, allowing a current to flow from the source to the drain. Under these conditions, the device behaves like a switch in its on state. If the voltage is not high enough to lower the barrier, there's no current, and the device behaves like a switch in its off state. There are two types of Mosfet, depending on the sign of the electrical charge flowing through it: NMOS and PMOS. In the first, the electrical current consists of electrons. In the second, it consists of holes. CMOS technology uses both types of Mosfet. The basic cell in this technology behaves like a pair of switches acting in complementary fashion. The name CMOS, complementary MOSFET, originates from this. Today's processors are manufactured by combining billions of similar structures.